Yeah, we're live.
Wonderful. Hello, everyone. My name is Yuri Dworkin. I'm an associate professor of electrical and computer engineering, as well as civil and systems engineering here at Johns Hopkins University. And today I'm going to be your moderator. It's a great pleasure to have here the gathering of people from both the academic and industry ranks, because one of the goals of the DC-MUSE is to promote this kind of collaborations. And our team at DC-MUSE, which comes from New York University primarily, as well as from affiliate universities all around the country, we are all very excited to this webinar, which is called System Perspective on Role of Hydrogen and Electricity in Industrial Decarbonization, because we believe that is a critical pathway for us to combat climate change and to find solutions that are going to be both value-adding and technologically feasible on the timescales needed for us to drastically change the way how our society deals with carbon. And today, I'm delighted to be joined by two great individuals. One of them is my former colleague at NYU, Dharik Mallapragada, who is an assistant professor. Dharik has a rather broad portfolio working on energy systems, and today he is going to bring in his perspective on the electrolytic hydrogen. Dharik and I are also pleased to be joined by Arana Venkatesh of EPRI, who is a senior technical leader. EPRI traditionally has played a great role in catalyzing the change in the electric power industry and, broadly speaking, in the energy industry. And we're looking forward to listen to what they both have to say. One important thing that I would like to remind you is that, as you can see on your screen, we have a QR code, and please do feel free to scan it and join our community on LinkedIn. You can get all of the professional updates from DC-MUSE. And in case of any questions regarding our engagement, you can reach out to the managing director of DC-MUSE, Simon Mashala, and to the director of strategic initiatives at New York University Tandon School of Engineering, Fran Balisi. Their emails are also shown on the slide. And without any further ado, I would like to introduce a very few housekeeping rules. We're going to give time to present to our speakers today. And the first speaker will be Dharik Mallapragada. The second speaker will be Arana Venkatesh. And after that, we're going to have a Q&A session. If you have any questions, we will ask you not to interrupt the presentation, but rather use the Q&A section. We will see the questions and we will moderate the panel. I also would like to ask you all to double check if your mic is muted. And if not so, please do mute yourself. And with that, Dharik, the floor is all yours. Please go ahead.
Great. Thank you very much, Yuri. And hello, everyone. Let me just get my screen up and running. Great. So I imagine everybody can see my screen. I think that is a yes. Great. Thank you. Good afternoon. Hello, everyone. And it's a great pleasure to be participating in this seminar to talk about some of the work my group has been doing in the area of systems analysis to understand the design, scale-up, and grid integration of electrolytic hydrogen production technologies and their critical role for economy-wide decarbonization. So we really see electrolytic hydrogen as sort of the first of potentially many electrified chemical and fuel production pathways that could play a pivotal role for economy-wide decarbonization. So understanding the pathways for scaling up electrolyzers could also provide several important lessons as we think about scaling up other electricity-intensive chemical manufacturing technologies. So I'd like to start by just sort of framing the context of this work, which is mostly around thinking about economy-wide decarbonization and looking at opportunities for understanding the decarbonization pathways for difficult to electrify sectors of the economy. Hydrogen as a molecule has received a lot of interest in this context as we particularly start to expand the aperture for decarbonization efforts beyond the power sector. So everybody has their favorite hydrogen chart. This is mine from the International Energy Agency that conducted a net zero by 2050 analysis a few years ago, where they sort of looked at the projected use of hydrogen across different sectors of the economy under a net zero pathway. And you can see that it goes from roughly 100 million tons of hydrogen consumed today to about 500 million tons of hydrogen by mid-century, mostly dominated by industrial applications as well as heavy-duty transportation applications. So when you sort of look at these numbers, one might concur that a five-fold increase in hydrogen production does not seem a very daunting challenge over a 3-decade time frame, given the relative scale of technology deployment we need for, say, power grid decarbonization. But importantly, it's worth noting that all of the nearly 100 million tons of hydrogen that we consume today is nearly entirely based on fossil fuel-based hydrogen production. So if we sort of put this in the context of low-carbon hydrogen production, then we're really talking about a much, much larger increase in the total production footprint for these pathways. So the challenge here is really quite daunting. Now, low-carbon hydrogen comes in many different forms, and that is one of the appealing features of hydrogen, the versatility of production pathways that exist for its production, as well as the many sectors that it can play a role in. So in today's presentation, I'm going to focus on electrolysis coupled with renewable electricity, either in sort of a islanded configuration or electrolysis connected to the grid to indirectly use renewable electricity also connected to the grid. But I just want to sort of frame that there's many other pathways that one could consider, and it's really sort of important to consider the competition between these pathways. So one approach that is an alternative to electrolysis would rely on performing carbon capture and sequestration to natural gas-based hydrogen production, which is one of the dominant production pathways today in many natural gas abundant regions of the world, including the US. Another approach would rely on using biomass-based hydrogen production, where we basically produce synthesis gas through biomass gasification, and through purification of that synthesis gas can produce high purity hydrogen, along with the potential to capture CO2, which would be biogenic in nature and thus represents a net negative process from an emission standpoint. And then there's the option of sort of thinking about more integrated electrolytic hydrogen production schemes that exploit high temperature heat available from current and next gen nuclear reactors, where you could basically use the heat from the reactors to not only convert water to steam, but also perform electrolysis at higher temperatures, which would overall reduce the electrical energy input needed for driving the reaction. So as I mentioned today, I'm going to focus on the islanded and grid-connected electrolysis systems, but there's really a portfolio of solutions here that one has to consider. And you'll hear from about the potential competitiveness of some of these pathways in the subsequent presentation from Aranya. So focusing on electrolysis, we see that there's been a sort of a rapid increase in the interest around deployment of electrolysis technologies over the past few years. So this is just showing you the global installed electrolyzer capacity by technology and region. But it's worth keeping in mind that the scale of deployment is relatively small compared to, if you sort of contextualize the scale of hydrogen production from conventional pathways based on fossil fuel utilization. Amongst the electrolysis pathways, we have alkaline electrolysis, which is nearly a century-old technology that has sort of been the dominant approach, but there's growing interest in alternative technologies, particularly proton exchange membrane electrolyzers, which is another class of low-temperature electrolysis, which has some appealing features when it comes to utilizing renewable electricity, primarily from its ability to achieve higher current density ranges, as well as its ability to produce hydrogen at pressure through differential pressure operation, which could be potentially important for many different end-use applications. Nonetheless, PEM electrolysis has some challenges, notably that it has a higher capital cost relative to alkaline systems because of some of the critical materials that are used, but also because of the membrane and the membrane electrode assembly makeup itself. So one of the questions we've been asking ourselves is, as we think about long-term scale-up of electrolytic hydrogen pathways, what would it take from a technology design perspective, but also from a techno-economic outlook perspective on for PEM electrolysis to become cost competitive and be sufficiently low cost to be viable for low carbon hydrogen production at scale. So one of the things we wanted to look at was to focus on the critical materials associated with electrolyzers. And iridium is one of those critical materials that is used for the oxygen evolution reaction. in PEM electrolysis. And so given the limited utilization of iridium and supply chains that exist for iridium today, we wanted to understand how rapid scale-up of electrolyzers would be impacted by iridium supply chain constraints. So here is an analysis from a recently published paper where we sort of explore the impact of iridium loading and the average current density of the electrolyzer and what it means in terms of the iridium requirement to meet a certain fraction of a projected hydrogen demand by 2030. And as you can see here, the heat map sort of represents the iridium requirements. And then overlaid on that requirement is these contour lines that sort of reflect potential supply scenarios, considering different growth rates in supply of iridium, considering recycling and with and without recycling. And so as you can see here, that modern PEM systems typically tend to be in the top left corner of this box, where we are operating at fairly high loadings and relatively low current densities of around 2 amps per centimeter square. And this does not really match well with the supply that we have for iridium, creating some challenges fundamentally in the short term regarding the scale up of this technology. So to be clear here, the challenge is not so much about the lack of this material, it's more about the scale up of the supply chain that could potentially represent a bottleneck. If we sort of project out forward, we see that as we're able to quickly scale up the supply chain and for iridium, we can see that the contour lines representing potential supply scenarios tend to overlap with where modern PEM systems are today, reflecting that we can actually catch up, but it's really about the rate of growth that we are anticipating for electrolyzer deployments that could potentially be a bottleneck. So pivoting to the economics of hydrogen production using electrolysis, fundamentally, it's a question about the cost of electricity combined with the capital cost of the system. And so if we sort of dig deeper into the cost of electricity, we really have to sort of recognize the various temporal dynamics of grid operations that are underway today. So here is an illustration from California, where I'm showing you the sort of the makeup of the generation mix over 1 week in October last year, and correspondingly the day ahead and real-time prices at one location in the grid, where you can see that there's substantial fluctuations in the electricity price, largely following the pattern of solar generation with low to negative prices in the middle of the day and very high prices approaching $200 a megawatt hour during the sunset and sunrise periods. So as we think about making chemicals like hydrogen and other derived molecules using electricity, one has to be cognizant about these grid dynamics and how they might affect the economics and design of the entire system. So to sort of provide a paradigm for thinking about this, my group's been developing a number of different methods, looking at design and analysis of chemical processes, considering some of these grid dynamics, where we try to sort of design keeping in mind the operation that is expected for these processes under grid interactive scenarios. So the goal here is to sort of do a cost optimal design and operations for these systems, considering the grid dynamics, but also considering some of the physics of the system. So in the case of the electrolyzer, we want to be able to understand the part load efficiency variation as a function of current density, as well as its sort of minimum and maximum current density ranges and power electronics requirements. So when you take models like this and apply it to the context of electrolysis systems, one can start to ask a number of interesting questions related to technology design, but also in terms of locational and future scenarios about the electric grid. So here I'm showing you the levelized cost of hydrogen as a function of a different maximum current density range of operation for PEM systems that are operating either in a static mode, whereby they're operating in a baseload manner, or they're operating dynamically, where they're sort of optimizing their scheduling based on information about grid electricity price variations from 1 hour to the next. This is for a location based in Southern California, where we have sort of just looked at 2021 prices. So the main takeaway here is that you can see that between static and dynamic operations, we see that even though a static operations leads to lower capital costs, the cost savings you get from dynamic operations in terms of operating costs tend to generally outweigh the capital cost increase that is resulting from underutilizing your electrolyzer. And this only tends to grow the higher current densities that you can operate your electrolysis system. So dynamic operation has some benefits in today's context, even with expensive electrolyzers and relatively high electricity prices with not too many instances of low prices of electricity. If you sort of now move forward in time and look at scenarios of the grid in the future, where you have increasing hours of low-priced electricity resulting from increasing renewables penetration, coupled with increasing hours of high-priced electricity that would be resulting from periods of limited renewables availability, you get a very different sort of distribution in electricity prices. And also, we would expect in the future, if we see cost reductions in the capital costs of electrolyzers, we find that the advantage of dynamic operation only tends to grow. So here is an example where I'm showing you the sort of the performance of a static PEM electrolysis system that can go up to that operates at 5 amps versus a dynamic PEM system that goes between 0 to 5 amps per centimeter square, where you can see the cost savings starting to grow in these cases. The second point I want to highlight here is that we also wanted to compare this against a future alkaline system operating under static conditions, given its relatively lower current density and challenges with respect to being able to maintain the turn down at relatively low levels. So here in this particular scenario, you see that we can start to sort of reach a point where PEM electrolysis under dynamic operation could be more cost competitive than alkaline systems if you're able to exploit the flexibility of this asset. So far, my presentation has focused on the cost perspective, but really we're interested here about producing low carbon hydrogen. So what does that picture look like for some of these scenarios? So here is just a summary table where we're looking at different electricity scenarios, and under all of these different electricity scenarios, based on the marginal emissions associated with the grid at each point, we compute the carbon intensity of the hydrogen produced. And as you can see, until we sort of get to very deeply decarbonized grids, we are sort of operating with hydrogen that is produced from electrolysis simply connected with the grid that may be very high carbon intensity. And this, to put some context here, is much in the top row is higher than the carbon intensity associated with natural gas-based hydrogen without carbon capture. So really the question here is that grid-connected electrolytic hydrogen production may not be very low carbon unless the grid is substantially decarbonized. So this question has taken on a lot more emphasis given recent policy incentives that have been sort of developed both in the US and Europe around low carbon hydrogen production incentives. And here the focus has been on trying to index these production incentives with the emissions intensity of the hydrogen that is being produced. So as an example, the US Inflation Reduction Act has a production tax credit that sort of rises as the carbon intensity of your hydrogen produced is reduced. So how do you measure this carbon intensity? Recent guidance provided by the US Treasury has suggested that the clean electricity to be used for electrolytic hydrogen has to meet certain criteria in order to be qualified as low carbon. These criteria pertain to whether you are adding more renewables to the grid, effectively bringing your own renewables to the grid, whether or not you're matching your consumption of electricity with the production of electricity from those renewables, both in time and space. So one of the questions we wanted to ask as a consequence of thinking about pathways to get to low cost and low carbon hydrogen is that what is the impact of some of these production tax credits with all these caveats when it comes to the costs and emissions of the low carbon hydrogen we want to produce from electrolysis. So we're going to focus on just the temporal matching component, which I think is an illustration of some of the challenges that come along when we think about coupling electricity-intensive fuel production with grids. So in order for us to think about this question, we have to sort of think about the nexus that results from having electrolyzers connected to the grid and indirectly sourcing electricity from the grid for those renewable electrons. So we have this picture right now where we have these three main components, but really when we start to think about adding any new loads or any new supply and trying to understand their emissions impacts, we have to think about the other elements that are at play here, particularly how this new load and new supply might impact the operation of the grid, but also incentivize or disincentivize the kind of investments that will be added onto the grid in the future. You have other renewables that might also be added onto this grid, but you also are having other loads, particularly loads from data centers, electric vehicles, and other end users that are being continuously added onto the grid. So when you sort of think about the question about the emissions associated with grid-connected electrolysis, we have sort of had to expand the system boundary to think about all of these interactions. One particular interaction that becomes quite notable is about the interaction in the supply side when it comes to the renewables that are available for utilization for hydrogen production versus the renewables that may be available for meeting other types of demands. Depending on the competition between these resources, we could have quite different outcomes when it comes to the emissions impact for electrolysis. So to illustrate this and quantify these effects, we need models that can capture all of these complex interactions, not just between representing the processes, but also representing the interaction between processes across different sectors. So one of the other aspects of my group focuses on developing these macro scale energy system models, and with the aim of making them available as open source frameworks that can provide a transparent assessment of emerging technologies as well as policies such as the production tax credit in the US. So I'm going to cut to the chase just in the interest of time to sort of summarize what we found from this particular analysis. So as I mentioned earlier, we focused our analysis on the temporal matching elements stated in the Treasury guidance regarding being eligible for the production tax credits. And so the two sort of suggested approaches have relied on hourly matching, which involves matching your electricity consumption associated with electrolysis with equivalent production of renewables in those hours. Alternatively, you can match this on an annual basis, where your annual consumption from for electrolysis would be matched by an equivalent amount of annual production from renewables. So in this particular chart, what I'm showing you is a computation of the consequential emissions impacts of adding hydrogen loads with these requirements under a range of technology scenarios involving different quantities of hydrogen demand, as well as whether the electrolyzer is operating in a flexible manner or in a base load manner. And the two panels that you see here reflect two different worlds of competition that exists between renewables that are being used for hydrogen and renewables that are being used for non-hydrogen applications. So under the compete world, we sort of assume that hydrogen is prioritized for renewables and sort of outcompetes other uses of renewables in the grid. Whereas in the non-compete world, we sort of basically presume that there is no competition between renewables for these resources, and we have abundant renewables, implying that the renewables that have been added onto the grid for hydrogen are truly additional. So what the big picture takeaway from these analysis, which you can see here, is that the consequential emissions impacts, particularly for annual matching, which is the less stringent matching standard, really depends on what your worldview of the competition for renewables is. So if you're in the compete world, where you believe that there's going to be competition for renewables between hydrogen and non-hydrogen applications, and hydrogen would be prioritized, then you can see a large displacement effect, which results in increase in emissions on the grid resulting from this adoption. Whereas if you're in the non-compete world, you see that opportunities for truly adding additional renewables into the system imply that you can get away with basically little to no emissions impacts for annual matching. So this creates some context and dilemma as from a sort of a decision maker standpoint to really understand which kind of worlds we live in and try to sort of set policies and rules that sort of reflect this evolving nature of the grid. So another piece of this sort of analysis sort of focused on trying to sort of ask the question, which I'm sure many developers have been very particularly focused on, which is around the cost impacts of these requirements. And so taking the same compete framework, we show that you can sort of try to understand some trade-offs that exist between the costs of hydrogen produced and the emissions impacts associated with those hydrogen production under these various requirements. So here I'm showing you this cost on the y-axis and the emissions intensity on the x-axis for different scenarios of electrolyzer operation as well as electricity sector decarbonization policies. So the first line that you see here reflects basically the cost differences between hourly matching and annual matching. where you can see that hourly matching being the more stringent standard leads to much higher cost than annual matching when you are assuming your electrolyzers are operating in a baseload manner, and when there is no other standard decarbonization policy for the rest of the grid. If we now go to a paradigm where we sort of introduce flexible operation of the electrolyzers, we see that the delta between hourly and annual matching substantially reduces, resulting from that flexible operation, so reinforcing the fact that we do need flexible operation. But there still remains that delta. But then the more interesting dynamics happen around the grid side, where if you sort of realize that the deployment of hydrogen is not happening in isolation, but we have policies that are already in place in many different contexts that are looking to decarbonize the grid, then those policies also interact with these production incentives, resulting in very different outcomes when it comes to the emissions associated with annual matching relative to the world in which you don't have any RPS policies. So the big picture takeaway from this is that really we have to think about the implications of some of these policies and their interaction effects when we think about the scale up and deployment of hydrogen production technologies that are interacting with the grid. So to just wrap things up, here are some key takeaways that I hope to leave you with. If you're thinking about electricity intensive operations, we really want to focus on flexibility at the operational level, which would be critical for enabling cost competitiveness and also supporting grid integration of renewables. As we think about low-cost hydrogen production, there's a number of levers that we can sort of employ to reduce the cost of hydrogen production, both on the capital cost side, reducing and indirectly reducing critical material use, as well as in the operating cost side. And then finally, as we think about electricity-intensive processes, carbon accounting becomes quite complicated, as I highlighted in the examples before, and one has to really sort of factor in not just the direct use of electricity, but also the consequential emissions impacts that come from adding new loads and new supply to the grid. So with that, I'll stop and just acknowledge that this is work done by my fairly extensive research group of grad students and postdocs, as well as the funding sources. So I'll turn it back to Yuri from here. Thank you.
Thank you. Thank you so much, Dharik, for this engaging conversation. And before I switch to Rana Venkatesh, I just want to remind you all that please do provide your questions in the chat box. And Rana, without any further ado, I would like to switch over to you. The floor is all yours. We don't see your slide deck just yet, so if you share it. Wonderful, thank you.
Great, can folks hear me now?
Yes, we can hear you well.
Perfect. So just wanted to say, thanks again for the invitation to present here today. I'm really excited to participate in this discussion. And also, it was really nice to hear some of the work that Dharik presented. And I think what I'm going to talk about today sort of nicely flows with some of the analysis that he shared already. I'll spend maybe 30 seconds on introductions. So as Yuri mentioned, I work at EPRI, and for those of you who aren't familiar, we're a nonprofit R&D organization. We were founded back in 1972, and we collaborate with about 450 companies across 45 countries across the world. And I work in the Energy Systems and Climate Analysis group, where we do a lot of research relating to decarbonization, policy analysis, planning, climate resilience, risk management, among sort of several other topic areas as well. And the work I'm presenting to you today is part of the Low Carbon Resources Initiative, or LCRI. So within LCRI, we do a lot of work in thinking about how to accelerate the deployment of low carbon technologies, which are important for deep decarbonization, especially when we're thinking about the 2030 and beyond time frame. All right, so what I'm presenting to you is a study that we developed back in 2022. And this was really a modeling exercise where we used energy systems analysis to evaluate a range of different alternate strategies to get to net zero CO2 emissions specifically for the US in this case, and then looking out to the 2050 timeframe. So as I mentioned, this was published back in 2022, so the results are already available, and I encourage you to look at more details, since I only have a little bit of time to share some of the results here. But sort of the motivation for this was that, there are really many different factors that could affect the transition of the energy system to net zero. And so what we're considering here is a set of what we think of as comprehensive set of assumptions. They're not meant to be exhaustive, to develop these hypothetical scenarios to get to net zero CO2 within the US by 2050. So we have three scenarios that we're focusing on. So one is what we call an all options scenario, where we have a full portfolio of available clean technologies, whether that's renewables, CO2 storage, hydrogen, nuclear, and so on. And then we have the second higher fuel cost scenario, where we assume higher costs for certain fuel types like oil and gas and bioenergy, as well as CO2 storage. And then we have this third scenario, which is our most restrictive scenario that we analyzed, called the net zero limited option scenario, where we assume that there's no geologic storage available. And then we also have limited biomass supply in that case. I will note quickly here that since this work was done back in 2022, it does not include the impacts of IRA credits, as well as EPA's more recent 111 rules for power plants. However, we've done, a lot of analysis following this report as well, and I have some of those resources towards the end of the deck here today too. Right. We developed this systems analysis using EPRI's regen model. This is an energy economy model that has a pretty detailed representation of electric sector capacity and dispatch. It also includes a representation of different end-use sectors like buildings, transport, industry, both on the technology activities as well as on the demand side. And then it also includes a representation of non-electric fuel supply. So things that traditionally would be part of petroleum refining or bioenergy production, gas supply, as well as potential new sources, including hydrogen, other synthetic fuels that could be derived from hydrogen, ammonia, and so on as well. And so these are all kind of the possible set of pathways that we consider within the systems modeling framework. But we do use an optimization approach where each scenario develops sort of the least cost approach and selects from these set of scenarios in order to meet the final energy demands, as well as to satisfy any sort of emissions target that we might impose. So in this case, some of these net zero emissions targets as well. And as I mentioned, we use our US regen model, which consists of these three different modules, as you can think of it. Electricity, end use, and then fuels, and then we actually kind of solve them iteratively, to get the convergence. And I will note that for this specific analysis, we divided the US into 16 different regions in order to kind of characterize differences in the supply of energy, current infrastructure limitations, other endowments and resources, as well as climate differences across the different regions. We assume that the different regions can be connected to each other by transport or transmission infrastructure, whether that's electric or hydrogen or so on. And one quick thing to note here, such an analysis obviously requires a whole host of input assumptions, including technology cost and performance, availability kind of assessments, and here we actually leverage the assessments that our colleagues within LCRI as well as other parts of EPRI do. And that's based on their extensive expertise in the area, as well as collaborations with EPC firms. I don't have a lot of time to focus on sort of detailed assumptions for the model, but I'll mention a couple that might be of interest, at least in the context of sort of industrial decarbonization. So in the industrial sector, we look at both manufacturing as well as non-manufacturing sectors. Within the manufacturing sector, we typically look at different end uses, whether that's process heat, whether that's, HVAC or machine drives, those sort of subsectors. And then we look at, alternate decarbonization pathways or technologies for those different subsectors. We do have a little more detail for some subsectors like cement and iron and steel. So for example, we include CCS as a possibility. We include electric arc furnaces and a couple of other technology types. And then a quick word on hydrogen as well. So as Dharik mentioned earlier, there are several pathways that we could have to produce hydrogen. And so we do incorporate some representation of that, whether it's biomass or gas, SMR with CCS, or electrolytic hydrogen. And on the demand side as well, there are a number of different places that low carbon hydrogen could be used, whether that's directly in the power sector, or it could be blended in the gas pipeline and used, in these end use sectors like industry and buildings. Or it could be converted into other products. So whether that's creating synthetic gas or synthetic fuels, or could be converted to ammonia. So that's just a very quick, I guess, introduction to the system framework as well. Sort of broadly, and I'll jump directly in the interest of time to this first slide of results that focuses on emissions across the different scenarios that we analyze. So here, this it's a pretty busy chart, and here we represent sort of total emissions by scenario, and each stack in the bar represents emissions contributions from the different sectors that we have. So whether that's buildings, transport, industry, fuels, or so on. And these, get the laser pointer up. Let me know if you can't see it, but you'll see these sort of red markers here, the circular markers that represent sort of the net CO2 emissions for the specific scenarios. So first here you have 2020. We also ran a reference case, with no net zero targets, and then we have these three scenarios that I mentioned earlier. And you'll see that even in the reference case, we see a significant reduction in emissions, and these are primarily driven by emissions reductions in the transport sector. So you can see that stack sort of reduce. And if you focus on the net zero results, you'll also see that there are sort of many different pathways to net zero. So in the all options case, where you do have the whole suite of technology options available, you do have CO2 storage as well. You do have positive emissions from these different sectors, which are offset by negative emissions in this case, mainly from biofuels with CCS. And as you get to more kind of the more stringent scenarios, you see that you need to reduce the positive emissions more and more, since we have the negative emissions offset are either expensive or they aren't available. And the positive emissions are, reduced in these scenarios using any of these sort of pillars of decarbonization you can think of, whether that's energy efficiency, electrification, or fuel switching going forward. I want to quickly, call your attention to two subsectors of fuels and industry. So the fuel sector includes also what we think about typically in industry. So it includes petroleum refining, hydrogen production, for example. And then the industrial sector are these more traditional manufacturing and non-manufacturing industries, as I mentioned. You can see that, in the all options case, there's almost, 45 to 60% emissions reductions just for those sectors. And as you get to the more stringent limited options case, you see, between 80 to 90% emissions reductions for those sectors specifically. Right. The next slide here talks a bit about what the economy-wide, final energy demand looks like for all these scenarios. And so I guess first off, quickly, one key takeaway from this is that you'll see final energy decreasing across the scenarios from the reference all the way to net zero, again, driven by, electrification or efficiency improvements in these specific scenarios compared to 2020. In 2020, Electricity was about 20% of final energy demand as a direct share, and that only increases as you get to these more stringent levels, so going up to 60% in this limited options case. You also see a higher penetration of synthetic fuels in some of these higher, in these more restrictive net zero cases. So for example, the darker brown here represents the liquid fuels mix. The lighter brown here represents the pipeline gas mix. In the all options and higher, fuel cost scenarios, much of the pipeline gas is just, fossil natural gas. Since you have the ability to offset some of those, emissions by using, sequestration. And the liquid fuel mix is sort of a balance of, traditional petroleum fuels as well as bioenergy fuels here. But as you get to the more, restrictive limited option scenario, you'll see the pipeline mix changes pretty significantly, shifting more towards using synthetic gas as well as renewable natural gas. And similarly, you see a larger uptake of synthetic fuels in the liquid fuels mix as well going forward, again, driven by the more restrictive constraints around that particular scenario. And so this really highlights the sensitivity of the role of hydrogen as well as e-fuels to what our assumptions are around CCS and bioenergy in this case. The next slide is a snapshot of electricity, both from a supply and demand perspective. As you can imagine, there's quite a significant increase in electricity demands as you get to more restrictive, net zero scenarios. In the all options and the the higher fuel cost scenarios, there's more of a contribution from gas with CCS or biomass with CCS in those cases as part of the portfolio of supply. But as you get to the more restrictive option, since you don't have storage available, you see a larger contribution from renewables as well as new advanced nuclear in those cases. And on the demand side, you see quite a significant increase in electrolytic hydrogen demand in that limited option scenario. Again, which helps support some of the low carbon fuels utilization in that scenario, as we saw in the previous slide. The next slide here provides a bit more detail into hydrogen itself, both on the supply side as well as on the demand side. If we look at the all option scenario, you'll see that most of the hydrogen supply comes from gas with CCS here, as well as a little bit of supply from biomass with CCS. Much of the hydrogen is either used directly in industry, or it could be blended into the gas pipeline up to I think it's a 7% energy limit that we assume, and then it's finally utilized in these end use sectors. In the higher fuel case, you see sort of a higher contribution now from electrolytic hydrogen, given that gas is more expensive in this scenario, and so you see that show up here. Again, given that gas is more expensive, you see sort of a smaller contribution from blended hydrogen in that case into the gas pipelines, but you see a larger utilization of sort of direct hydrogen use here in the gray. And then finally, in the limited option scenario, since we don't have access to CO2 storage, you see a significant contribution from electrolytic hydrogen on the supply side. And on the demand side, you can see that much of the demand is now driven by the synthetic fuel use here in the blue. Actually, one last slide on just a sort of deeper dive into what's happening sort of within the industrial sector itself. As I mentioned earlier, we look at both manufacturing and non-manufacturing. And then within manufacturing, we look specifically at process heat and steam, as well as these other manufacturing processes that include things like machine drives, HVAC, and so on. On the other manufacturing side, many of the processes are either already electrified or can be more cost effectively electrified. And so you see sort of an increasing electrification trend as you get to more stringent net zero scenarios here. On the process heat side, again, we have some limitations on electrification. While some, electrification of process heat might be possible, there's generally, a stronger reliance on low carbon fuels in this case, as some, direct hydrogen use, some synthetic fuel use as well, along with, some carbon capture for sort of larger point source industries like cement in this case. So I'll pause there in terms of slides, in terms of results from this analysis in the interest of time, but I just wanted to, kind of share, some more background information as well as related research that we've done in the past couple of years, to this area. There's an extensive amount of work we've done within our group, thinking about systems analysis, thinking about deep decarbonization targets as well. And I encourage you to kind of, look those up when you have a chance. And I also wanted to, quickly give a shout out to some of the other activities that are going on within LCRI that aren't necessarily focused on systems analysis, but there's a lot more around thinking about techno-economic assessments, collaborations with other partners who are working to think about accelerating the deployment of these technologies, both from just focused on hydrogen as well as thinking more about net zero integration in the context of the industrial sector as well. So I'll leave these two slides up. I encourage you to reach out to both Neil and Tracy, who are listed as contacts here for more information, and happy to take questions.
Wonderful. Thank you so much for your presentation, Narana, and thank you so much for your presentation, Dharik. And just to kick off our conversation, while you all are typing your questions in the chat, I would like to ask my first question as a moderator to Dharik. Maybe also informed in part by what Narana put into her talk. Dharik, would you comment on non-technical barriers? Because in the chat, we have a lot of technical questions. Can electrolyzers be operated flexibly, for example, or can they potentially bump into some other technical difficulties? What are the non-technical barriers? Because it feels that a lot of things that we have to address before electrolytic hydrogen can become like an industry scale technology lies in the space where engineers need to collaborate with other field of practitioners. So how would you feel about it?
Yeah, so thanks for the question. And I think it's very insightful to sort of reflect on this after Anya's presentation, where you sort of get the full picture of the economy. So one thing I would highlight is that, and this has been highlighted by several other studies, including by the Department of Energy, is that we really have a challenge of demand creation around low carbon hydrogen demand, particularly in the US context, where a lot of the policy incentives are very supply side focused. And so when you think about sort of actually penciling out large capital investments around electrolytic hydrogen production projects, you need to have some offtake agreements to be able to sort of guarantee that that investment will have a return. And I think currently the sort of the environment that we have doesn't have enough sort of natural incentives to sort of adopt hydrogen, particularly low carbon hydrogen, given the sort of the environment that we live in, where we have relatively low cost natural gas for making hydrogen. So I think that remains a key non-technical barrier that needs to be reflected on, which also includes some technical challenges when it comes to adopting end-use hydrogen, infrastructure challenges, say in transportation for fueling, but also in industrial applications.
Thank you, Dharik. And maybe again, going back to one of the questions on the chat, which draws on international experience. Aranya, I would like to ask you, what are the key insights that you feel would be most important for us while taking regional impacts into account here, whether it's within the country or how we can learn what happens in one region and translate this learning into another region, or internationally, like EU is a big example. Somebody in the chat mentioned experience of other countries. So to what extent should we learn the internalized experiences from interregional scale?
Yeah, that's a great question, Yuri. We've done a little bit of modeling work in other countries, also thinking about net zero in other regions as well. But I think there's two ways we can get some insights just based on the work that I talked about today. So one, the set of scenarios we looked at, where we looked at, scenarios, for example, with limited CO2 storage, higher fuel supply, those kinds of scenarios could reflect, several other countries right across the world. And so some of the insights we find for those specific scenarios could translate. So for example, with limited storage and limited bioenergy, you'd see perhaps more of a reliance on low carbon fuels. If there's not sufficient resources in order to support that production, domestically, that's when you start thinking about imports. And a lot of countries across the world are thinking about low carbon imports, low carbon fuel imports as well. The other way we can think about sort of this, regionality aspect is if we look at some of the results that we have for the individual regions that we model within our study. And there's a nice report that some of my colleagues published last year that does a deep dive into the different regions. And they came up with a list of some factors that are really important, right, and drive differences between regions. So one is thinking about the endowments in a certain region, whether that's in terms of existing infrastructure, existing gas infrastructure storage, as well as how good the wind, solar, and other resources are. So that obviously drives differences across different regions. There's also something to be said about the policy landscape in certain regions. So for example, in regions like California, in some parts of the Northeast, where you have stronger policy drivers, you'd perhaps see sort of a slightly different unfolding, I guess, of the energy transition, going forward. One of the interesting results from the regional deep dive was that, a lot of the supply ends up being concentrated in regions with really good resources. So for example, in areas like Texas and in the plains where you have good wind resources, that's perhaps, places where you can support low carbon, fuel supply. But that doesn't mean that's where it's utilized. It ends up being transported to other regions and utilized as well. So again, sort of an insight we can look at, being able to translate to the international stage as well. So are there regions that, will exports become sort of an important factor as we think about deep decarbonization across the world? And how's it going to be driven by local policy context? How's it going to be driven by sort of resources that are available in those regions as well?
Wonderful.
That answers the.
That's perfect, Rania. And I would like to invite everyone else. Please do keep asking the questions in the chat. In the meantime, I want to piggytail on your answer, Rania, and maybe move a conversation a little bit on better understanding from your industry viewpoint. What would be the best energy carrier for hydrogen? Because I would imagine that this answer to this question would be deeply regional. And have you or your colleagues at EPRI looked into the way to proliferate hydrogen use and bring the cost down by minimizing stranded cost of existing infrastructure? Because the stranded cost will drastically differ, whether it's taxes, for example, as you mentioned in your answer, or it could be some other part of the country which does not have traditionally strong hydrocarbonate industry. So have you looked into that, or there is an opportunity to look into that?
Yeah, I want to say that there's a lot of work going on within LCRI, the initiative that I mentioned, that's looking at sort of the competitiveness, both from a cost point of view as well as from a feasibility point of view, especially in the context of exports. And especially in the context of, for example, local policy incentives that are available. So, for example, some of the work that we did as part of LCRI more recently has looked at how IRA can change the competitiveness of low carbon ammonia as well as e-gas, and we see that in some cases it could reduce the costs by up to 50% if you were able to leverage those incentives, whether that's for local use or for exports as well. So I think a lot of it will, like you said, depend on sort of the policy context more regionally. But I think there's a lot of work being done within LCRI, and I sort of invite folks here to kind of look at those studies as we roll them out over the next year or so. Oh, I think you're
wonderful.
Okay.
Yeah, thank you, Rana. Really great and comprehensive answer. And, one can ask so many questions that a smart person would never be able to answer. But despite that, you managed to pinpoint exactly the issue. It's how we transport and how we adaptate hydrogen transportation to the needs at hand in a given region. We are about to end this webinar. We have about 5 minutes left. I don't see any new questions in the chat, but I would like to ask a question across the spirit of this webinar when we're trying to build bridges between the industry and academic viewpoint. And I would like to ask both you, Arana, and Dharik, what did you learn from one another's presentation? So Dharik, maybe you go first and share with us what was the most insightful and interesting aspect of Arana's presentation that enhanced your view of the problem.
Yeah, thanks, Shuri. So I think, one thing as a fellow energy systems modeler, it's always interesting to sort of see how, the perspectives that you get from the results you see are highly dependent on what you include in the model versus what you exclude in the model, right? And I think, through the sort of the various scenarios that I think Aranya had set up around all options to limited options, you can see how the portfolios on hydrogen in particular, which I thought was quite interesting, changed quite dramatically, going from, very dependent on gas with CCS-based production in the, if I remember, in the all options case, to the sort of the electrolyzer heavy production in the sort of the limited options case, right? So highlighting really, I think, two things, right? One is, to me, there's a regional element of, when those scenarios will materialize, but then there's also, I think, a question of, as we're all doing our modeling here, to sort of think critically about, the assumptions and the system boundary we are defining when we sort of look at some of these results. And I think that, that was a great illustration of that point.
Thank you. And for you, Arana?
Yeah, thanks, Dharik. And I think I would highlight something similar for your analysis as well. I mean, really thinking about not just system boundaries, not just in the context of this sort of spatial system boundaries, but also temporal boundaries, and how, not thinking about those more comprehensively, could have these unintended consequences in terms of, increasing emissions in certain cases, especially as we're thinking about, the rollout of new technologies, both from the supply side as well as from the demand side, trying to grow demand in some of these new technology areas. So I think, thinking about the system boundaries more comprehensively could be important, of course, for policy discussions, but it could also be important for decision making from industry, right? So, for example, if you go into a new area to set up, new facilities, greenfield facilities, areas that don't have both supply or demand infrastructure that exists, how do you make sense of, which sites may be preferred over the others, right? How do you make sure that you're not looking at it through sort of a really small lens, but ignoring some of these system-wide impacts. So I think it just highlights the importance, both from from a decision-making context more broadly, to be mindful of these system boundary challenges.
Thank you, Arana. And in the remaining 1 minute, I just want to say that to me personally, as a moderator, one more point from the comment of Aris Marunian resonated strongly. It's a point about keeping in mind that we have both centralized and decentralized solutions to enable hydrogen proliferation. And I think it's important to keep that in mind in the context of both the Dharik's presentations and the Arana's presentation, because in different situations, centralized and decentralized solutions can work differently. One will take advantage of the economy of scale, the other one will take advantage of easier logistics and simpler simplifications. With that concluding note, I would like to thank everyone for attending this seminar. And as a reminder, please do take a copy of this or screenshot of this QR code and stay in touch with DC-MUSE over LinkedIn. We have a robust lineup of speakers for the seminars between industry and academia in coming weeks and months. So we're looking forward to hearing back from you. Thank you all and have a good day.
Thank you.
Thanks, everyone.